So we're going to do some examples from 1.1 today. Moving past the comparing two cars and the mathematical modeling, on to example 1. The time it takes you to get home from a football game is related to how fast you drive. So the faster I drive, the less amount of time it's going to take me to get home. I think that that's pretty intuitive, right? The slower I drive, the longer it's going to take me to get home. The distance is the same. Doesn't matter. From the school to my house, for example, is 20 miles. So if I go 20 miles per hour, it's going to take me an hour to get home. Yikes. So if it's 20 miles and I go in 1 hour, 20 miles, right? I just inverted the 20 miles per hour ratio. Oh, well, that's going to take me 1 hour, as we just said. However, if I go those same 20 miles and instead I drive 60 miles per hour, so 1 hour, 60 miles, it's going to take me 1/3 of an hour, or those 20 minutes. So using unit analysis, I can figure out that the faster I drive, right, the less amount of time it's going to take me. But you already knew that. Okay. So we're going to sketch a reasonable graph showing how this time and speed are related, and we'll give the domain and range of the function. I guess we should start by thinking about what's dependent on what. So in this situation, the time that it takes me to get home seems to be dependent on my speed, because the faster I go, so the higher my speed, the less time it's going to take me to get home. Now that's really important for this graph, because normally when I think about inputs and outputs, I think about time being my input usually. Most things are related on time. But in this situation, the independent variable is actually my speed. So I'm going to put speed along the horizontal axis, and I'll put the time that it takes me to get home on my vertical axis. So again, the slower I go, so the closer I am on my horizontal axis to the origin, right, the longer that time's going to take. Now, I'm not going to not get in my car and drive, so being actually on the y-axis wouldn't make any sense, right? So there shouldn't be a point on the y-axis. Otherwise, I'm just sitting in my car at the school forever. Okay, so I'm never going home. All right, now, obviously, the faster I drive, the less amount of time it's going to take me to get home. Hopefully, I'm not speeding and getting a ticket. Okay, but that seems like a good point there. Okay, or maybe that's going to be my 20 minutes. I don't have any units along my axes, so it doesn't really matter where I put these. I'm going to actually make an input-output table to help me understand if there's a constant rate of change here. So inputs are speed in miles per hour, and outputs is time. And how about I'll do that in minutes? I think that should work. So when I'm going 20 miles per hour, it takes me 60 minutes. Let's do something in between 20 miles per hour and 60 miles per hour. How about let's go 40 miles per hour. If I do 40 miles per hour, so 20 miles, 1 hour and 40 miles, that's going to end up giving me 1/2 hour or 30 minutes. Okay, so let's see, so then I'm going to have 60 miles per hour, giving me 20 minutes. Okay, so I don't think that this is a constant rate of change, and we're going to do a little bit more of this, but you can see that along my inputs, I'm constantly changing by 20, right? So I added the same amount to my inputs, but look what's happening to my outputs. I went down by 30, and then I went down by 10. That's not a constant rate of change, so my slope is not the same the whole way. It looks like the slope is becoming less and less as your speed increases. So this is going to be some kind of a curve. All right, so let's talk about domain and range. So the domain is going to be all the sets of my speed. Well, yeah, can I go as fast as I want? Sure, I can. I don't think that's a good idea. You'll probably get a ticket. You'll probably get in a lot of trouble. Domain. I'm going to use the variable s. Oh, maybe I'll do that. I'll label these s and t. All right, so first of all, we already talked about the fact that I can't go 0 miles per hour because that would just make me be at the school the rest of my life. So I better go faster than 0 miles per hour. So S has to be greater than 0 miles per hour. But let's see, let's say that just to be on the legal side, it needs to be less than or equal to whatever the speed limit is. How about that? Okay, now let's figure out the range. Well, the range is the different times it can take me to get home. So if I'm going really fast, it's going to take me less time to get home. If I'm going really slow, it's going to take me more time to get home. So it's these times along the vertical axis. So the least amount of time it's going to take me to get home, I'm going to assume would be when I am driving the speed limit. So I'm going to mark this spot along my horizontal or my s-axis, and that's going to be the speed of the speed limit. Now, could I in reality drive faster than the speed limit? Yes, you can. I don't recommend it. However, you totally could. So you can go as fast as you want or as fast as your car would let you, in which case, this function, this graph would continue. And the faster I go, the less time it takes me to get home. And then conversely on the other side, right, if the slower I go, I could go half a mile an hour and it would take me forever to get home. Okay, so I could come up with all kinds of weird scenarios. However, for this problem, I'm going to assume that I'm driving the speed limit. I'm going to assume that the time that it takes me to get home, well, the least amount of time it would take me is if I'm going the speed limit. So it's whatever this amount of time, this amount of minutes or hours is. And it's everything greater than that. Okay, so we'll say that t has to be greater than or equal to the time it takes driving the speed limit. We'll play it safe here. But now this brings up another great point. Well, this function, if I were to actually model this using a function, look at what's happening. I'm never touching my horizontal axis, which would mean that I have a horizontal asymptote. And I'm never touching my vertical axis, which means I have a vertical asymptote. Which function would give you both asymptotes? So I'm going to look at my parent graphs. All right, I got to find some functions and have some asymptotes. All right, so logarithmic functions have asymptotes. Well, they have vertical asymptotes. Exponential functions, we've already talked about, those have horizontal asymptotes. Well, which function has both a horizontal and a vertical asymptote? Could it be rational functions? Right, those rational functions have both a vertical asymptote and a horizontal asymptote. And you may be saying, but Miss Frisk, this graph does not look the same as the graph that we have in this problem. Basically, we have a restricted domain. We know that our speed needs to be bigger than 0. So we know that our speed needs to be to the right. It needs to be over here of 0. And then we know that our range, it needs to be some positive value, right? So it needs to be up here somewhere. Well, what does that define? That defines the first quadrant. So based on those restrictions in my domain and range that I've defined, couldn't it just be this branch right there? So this would be a rational function. So if you were going to model this, you would have to come up with a rational function. You'd take a few points, you'd do some regression, you'd get yourself a function. I copied problem number 2 out of your textbook, so let's go through that problem. It's about gas temperature and volume, and when you heat a fixed amount of gas, it expands, increasing its volume. In the late 1700s, French chemist, I'll call him Jacques Charles, used numerical measurements of the temperature and volume of a gas to find a quantitative relationship between these two variables. Suppose that these temperatures and volumes have been recorded for a fixed amount of oxygen. And I can see the numerical representation of this data over here in this table. So we're going to end up using that. We have a picture here of a hydrogen balloon, which was invented by Jacques Charles, and he participated in the first manned balloon flight in 1783. I don't know how many of you guys plan on someday taking a hot air balloon, but seems like a fun thing if you're not scared of heights. Starting with A, on graph paper, plot V as a function of t. Well, let's even see what these variables V and t mean. So if I look at my table of values, it looks like my inputs are t, and that's in degrees Celsius. That one's pretty straightforward. And then my outputs are V, which I'm believing to be volume, and in some units that start with an L, so I'm going to assume liters. Now they said that V is a function of T. We know that our inputs are T, or temperature, our outputs are V. So I know that my function actually can be written as V of T. Okay, that kind of helps me like name the function and understand what's going in and what's coming out. So I've given us some graph paper below, and that's where we're going to plot our points. Let's see what else this says. We're going to choose scales that go at least from, okay, so we need temperature to go from negative 300 to 400. We need volume to go from 0 to 35. We don't need any negative volumes. In order to make everything fit, I'm going to, on the t-axis, or the temperature axis, which again is in degrees Celsius, and on my volume axis, which again is in liters, I'm going to have to skip some units here. So I think on my temperature axis, because I need to go from negative 300 to positive 400, I'll go by 50s, but I'll skip every other one. So I got 100, 200, 300, and 400 degrees Celsius. And then going in the negative direction, negative 100, negative 200, and negative 300. All right, and then I'm supposed to go up to 35 for the volume in liters. I think I'll go by 5s, but I'll do the same type of thing where I skip every other one. So we'll actually do 10, 20, 30. I'm going to go up to 40 just so 35 is included. All right, let's read the rest of our directions here. All right, you should find that the points lie almost in a straight line. Okay, so we got to plot these points. So we're going to plot each and every point, and we're going to have to approximate some of these. So I think it was 0, 9.5, 50, 11.2. You should be making these approximately in a straight line, but we're going to make a line of best fit. So I'll talk more about that in a minute. Let's plot these. 100, 12.9, 150, 14.7. 200, 16.4. 250, 18.1. 300, 19.9. With a ruler, construct the best fitting line. The best fitting line you can for these points. So when we create a best fitting line, we try and draw a line through as many of the points as we can, usually attempting to get the same number of points above and below the line, or to the left and to the right of the line. That looks like a pretty good best fitting line. However, let's see, I was only supposed to extend the line to the left until it crosses the t-axis, and to the right to t equals 400. All right, so I've got it crossing my t-axis a little bit after negative 200, and I've got it a little bit past t equals 400. I think I'll delete a little bit of this line, getting me back down to basically what I think looks like the point 425. So part B, from the graph, read the approximate volumes at t equals 400. Well, I just identified that at 400 degrees Celsius, I have about 25 liters. I think I'll put B over here. And I'm going to write this in function notation. So V of 400 is approximately 25 liters. And the other one that they wanted me to do was at t equals 30. So let's see, V of 30 is approximately, I'm going to have to approximate this, so it's about here. Let's say it's about 10 liters. All right, next we're going to read the approximate temperature at which V equals 0. So V equals 0 at the X or the T intercept. So I think we were back here. And that looks to be about negative 230, let's say. So V equals 0 at T being approximately negative 230 degrees. How does this temperature compare with absolute 0, the temperature at which molecular motion stops? I'm curious. I don't know much about absolute 0, so guess what we can do? We can Google it. So looking online, I just Googled absolute 0. The first one was Britannica that came up, and absolute 0 is a temperature at which a thermodynamic system has the lowest energy. It corresponds to negative 273.15 degrees Celsius. Interesting. And that's negative 459.67 degrees Fahrenheit. Okay, so that's really cold. It was negative. So we're about 43 degrees off. Why might that be? Well, let's see. I had these points that were exact, and then I tried to approximate them here. Right, and then I drew a line of best fit, which we could probably do this many different ways. I did my best to get as many points as I could and try and have equal points above and below the line. Okay, so it's not exact, but it's close. Looking at C, finding a value of a variable beyond all given data points is called extrapolation. Extrapolation means beyond and pole comes from the pole or the end. Okay, so beyond the end. Finding a value between two given data points is interpolation. So in between, so that's between two given data points. Which of the three values in part B did you find by extrapolation and which by interpolation? Well, extrapolation, we went beyond the data points, we went beyond 300 degrees Celsius, right? So extrapolation was at the 400 degrees mark. And also, we went beyond this data in the negative temperature direction because we were only given data that started at 0, and we went all the way backwards to negative 300. One more time, which of the three values in part B did you find by extrapolation? So I actually think there were two values there. So one of them was the V of 400. And the other one was when V of t had to equal 0. And then our interpolation means in between the given points. So as long as we were somewhere in between 0 degrees and 300 degrees, we were interpolating anything that wasn't given to us. And so I think that would be our 30-degree point where it came out as 10 liters. So V of 30. D, why can you say that volume is a function of temperature? So remember the definition of function. For every input, there is one and only one output, right? So we can say that volume is a function of temperature because for every input of temperature, I only have one output of volume. Is temperature also a function of volume? Explain. Well, is there one and only one temperature for every single volume? So, for example, if I look at a volume of 20, yeah, there's only one temperature. I don't know, it's a little bit past 300, right? Or if I look at, 10, a volume of 10 liters, yeah, there's only going to be one input, one temperature that corresponds with that. So we can say yes. There's one and only one temperature for each volume. Which you probably don't remember this right now, but you're going to. This makes us an invertible function, which means that this function, when you do the inverse of this function, it's also a function, which you should remember because it passes both the horizontal and vertical line test, but that'll be coming up, and we'll review that again. All right, moving on to E. Considering volume to be a function of temperature, which we've already been doing, write the domain and range of this function. All right, so the domain I think we have to be higher than the absolute 0 in this situation. So I think that we can say that our temperature can go anywhere above negative 273 degrees in order for there to be a volume. In which case our range well, the volume has to be greater than 0. All right, we are done with the notes. Exploration in class.